Hey Geometry. We had a really good lab the other day, looking at parallel lines and what place you are and who's congruent to who and who is supplementary to who. And so what this lecture is focused on is sections 3.3 and 3.4, so from parallel and finding parallel all the way through perpendicular. I want to do a little lab review. Today we're going to talk, the first part of this lecture is about proving lines parallel, then constructions, then we're going to go into proving perpendicular and returning exams. I have no idea what that's about, but it's written there, so we're just going to go forward. So in the lab the other day, I had you set up in 8 different corners locations, right? And basically you figured out who your buddy was, and then I said, well, if these two lines are parallel, and let me get out my little marker here, and let me just ask a question. See, Haley, what color do you want? Purple? Okay, we'll do purple. So Haley said she wants this purple, and I'm trying to draw left-handed. That's supposed to be an arrow to indicate that these are parallel. Well, the moment you say that these lines are parallel, then you know right off the bat that 1 and 5 are corresponding angles and they're congruent, right? 2 and 8 are alternate exterior angles, so they're congruent, right? You have all these properties that take place. And that's just wonderful. Well, what does that mean? So when we look at conditional statements, we've got this block of conditional statements that says things like, if you have parallel lines, then corresponding angles are congruent, right? If you have parallel lines, then alternate interior angles are congruent, right? And I mean, you get the idea. There's these 4 patterns that come out of this, that alternate exterior, alternate interior, corresponding angles are all congruent. And if they're on the same side and they're interior, then they're supplementary, right? In this pattern, if you have, I'll use that purple again. Wait, Ren said, no, don't use purple, make it green. All right, I'll do green just for Ren. Right? So now we've got these lines are supposed to be parallel. If you have parallel lines, then all these relationships are true, and essentially you're down to 2 angles. There's an acute angle and there's an obtuse angle. Well, what I want to focus on today is, well, what if you don't know that those lines are parallel in the first place? What if you come in here and you say, well, wait a minute. I know angle relationships. What does that tell me? So when we talk about a converse, again, in a conditional statement, if P then Q, the converse of that means to switch the conclusion with the hypothesis, and you get if Q then P. So, I know drum roll. Should we do drum roll? The first one, if the corresponding angles are congruent, then the lines are parallel. If the alternate exterior angles are congruent, then the lines are parallel. If the alternate interior, alternate exterior are congruent, then they're parallel. And if same side interior angles are supplementary, well, guess what? Then those lines are parallel. And that's the first part of this whole lesson, is to say, wait a minute, the converse of those theorems or postulates are also true, right? So the real question is whether it's given that the lines are parallel or not, or perpendicular or not. That's the big idea. So here in this problem it says, hey, let me move my mug out of the way. There we go. It says, use the converse of corresponding angles postulate and the given information to show that lines L and M are parallel. All right. Well, it says the measure of angle 7 right here is this algebraic expression. The measure of 5 is this one. And x is 13. Well, wait a minute. All I got to do is 5 and 7 are corresponding angles. I have to make them supplementary, or congruent, which means set them equal to each other. And then, get my face out of the way. Good gravy. Plug in 13 for x and see if it's true. If it's true, and guess what? It is true. 77 does equal 77. Then lines L and M are parallel by the converse of the corresponding angles postulate. If you did your math correctly and these numbers were not the same, then guess what? Those lines ain't parallel. All right, tons of examples of this in the real world. And the piece here is to say, hey, when you're working with patterns, again, same kind of problem, how do you know that these 2 pieces of wood are parallel? Well, I've got an expression for angle 1. I've got an expression for angle 2, but what's different? What kind of angles are angle 1 and angle 2? Hold on, let me, go ahead, shout out. Lucas, what was that? You're right, they're supplementary. So when you look at this problem, you're going to say, oh wait, 1 and 2 aren't equal. 1 and 2 add up to 180. And so if I can prove that 1 and 2 add up to 180, then A and B are parallel by the converse of same side interior angles are supplementary. And in fact, that is what we have here. When you do the math, you find out that they do add up to 180. So that's the big part of that lesson. Now, we need to get into constructions, but the reality is you guys know how hard constructions can be if you're trying to follow along. So I'm going to work with you in small groups. What you do need to know is this following postulate, which says through any point not on a line, there's exactly one line parallel to the original line. And the same is true with perpendicular. If you have a line and you have a point outside of it, there's one line perpendicular, there's one line parallel. All right? So we're going to do that in class, so don't stress about it now. Let's keep it simple. All right? So again, we said if we have parallel or perpendicular, then we can assume certain things. Now we're getting into if we know certain things, then we know that they're parallel or perpendicular. And this is my picture here. Does anyone know Tower Bridge? Okay, this is Tower Bridge in London. And again, clearly those are beautiful perpendicular towers. So the point here, let me again get my face out of the way. Sometimes it just gets in the way. We talked about bisecting segments before. And I need to emphasize that that segment that bisects it is also perpendicular. Okay, well, what's the significance of that? Well, the shortest segment, let's just read it together. Aaron, would you read it for me? The shortest segment from a point to a line is perpendicular to that line. Okay, that in fact is the definition of the distance from a point to a line, right? If you want to figure out how far away this dot is from this green line, you're not going to go straight down, right? You're not going to go here and say, hey, how close are we? We're down here. No, you're not going to go over here. No, you're going to go perpendicular. You're going to make sure that that's a 90-degree angle because it is in fact the shortest distance between a point and a line is the perpendicular path through that line. Make sense? Yeah, but now what does that mean is the big question. Okay, so when it says name the shortest segment from point A to BC, let me ask Thomas here. Thomas, what color do you want? You want to do red? Okay, we're back to red. What is the shortest segment from A? Remember, A is just a point to BC. Well, the shortest segment would be AB. And I'm trying to write left-handed with a mouse. Oh man, that's just brutal. But I think you get the idea. The shortest segment, because it is perpendicular to BC, is that one. Okay? Now, when it says write and solve an inequality for x, guess what? AC has got to be greater than AB. That's true, right? If this is the shortest segment, then we know 12 has to be greater than x minus 5. 12 is greater than x minus 5. You do your math, you add 5 to both sides, plus 5, plus 5. You get 17 is greater than x. Another way to put it is x has to be less than 17. That's what they're asking for you in these kind of problems when it says, what's the shortest segment, and then figure out what the value to make that work. I'm at 8.5 minutes. You guys hanging in there? Give me a thumbs up. Good. All right, you have these theorems in your notes. I made you already get them down. The first one, of course, says if two intersecting lines form a linear pair of congruent angles, well, guess what? Those have to be 90-degree angles. Therefore, those lines are parallel, or perpendicular. Woo! The second one says if you have parallel lines and one of the intersections is perpendicular, then the other one also has to be perpendicular. And the last one says if you've got a line that's perpendicular to two other lines, that means those other lines have to be parallel. I mean, that's all quite reasonable, but let's see how it plays out. So here, oh yeah, back to proofs. Write a two-column proof. Given that angles EHF are congruent to HFG, EHF and HFG, good, and that FG and GH are perpendicular. All right, so what they want you to do is prove that EH and GH are perpendicular. Well, wait a minute. If I knew that these two lines were parallel, that would make life a lot easier, because if this one's perpendicular to that, then it's got to be perpendicular to that. Well, actually, that's what we're going to do, because step number 1, statements on the left, reasons on the right. Step number 2, when it tells me that these angles are congruent, that's important. And that's my first step, is to say, I know it's a goofy looking symbol, but get over it. It's all I can do with a keyboard. That's given information. These two angles are congruent. Well, what kind of angle pair are they? Let me ask, hold on. Joseph, what are they? Yeah, very good. They are alternate interior angles. Well, how do you know that? Well, by definition, that's what alternate interior angles are. They're cut by this transversal from F to H. Well, sweet. Now that you know you've got congruent angles that are alternate interior, that means lines EH and line FG have to be parallel by the converse of alternate interior angles. Oh man, now it's getting good. Because, so what? Well, now that you know those two lines are parallel, you know that line FG, oh wait, I'm sorry, let's restate the obvious because I never stated it. FG is perpendicular to GH. That was given, right? You say I'm doing this a little out of order, but you follow my logic. Now I know that EH has to be perpendicular to GH because of the perpendicular transversal theorem that was just on the previous page. Again, if you need to go through it one more time, just rewind. That's okay. I'm already at 11 minutes. It's getting long enough. Sometimes we get other examples here. For example, getting caught in a rip tide is not a good thing, and they always say swim perpendicular to it. Well, why should the path of the swimmer be parallel to the shore? Well, if the riptide is 90 degrees perpendicular from the shore, and you take another 90-degree turn, you just ended up going parallel, right? And if you read through the problem and say, oh yeah, that makes a lot of sense. What a great day. Could you ask for a better lecture? Proving lines parallel, proving lines perpendicular, using perpendicular, the shortest distance between a point and a line is a line perpendicular to it. Have a good one.